Well, I think Audric will join us before we know it. I've left my volume on, so hopefully I'll hear him when he comes in. Find my markers. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to just bless our work today. Help us to understand a little bit more about Lie Algebras and how to understand them, Lord. In your name I pray, Lord Jesus. Amen. All right, so I am in, again, working through bits and pieces of Erdmann and Wilden's Introduction to Lie Algebras text. Last time we more or less covered chapter 1. And I think there's there's various things in there we'll need. Of course, the definition of Lie algebra, we need to know that. But the other thing that I should probably put down for us is the definition of, well, obviously the center of the Lie algebra, we need that sometimes. What's the center? So the center of a Lie algebra, Z of L, is x in the Lie algebra such that the bracket of x and y is equal to 0 for all y in the Lie algebra. So this is the so-called center of the Lie algebra. It's an ideal. All right. And then the other thing that probably should remember is the derived. Where'd that thing go? I thought we had the set of derivations. Okay, but that's not the derived subalgebra. Huh. All right, well, never mind. I was thinking something else. I guess I was wrong. So we'll be in chapter 2 then. Let me close this door here. That's probably them leaving. So you remember an ideal is a what? So I is an ideal of Lie algebra L if I is a subspace, right, of L, and you have that xy is an element of the ideal again for all x in L and y in the ideal, right? So it's got that, as we've called it, like uber closure, if you like. And so there are a number of important ideals you can form. So given two ideals, say I and j, you can form I intersect j and also I plus j, and these are new ideals. I plus j is just defined to be the set of sums, right? X plus y such that x is in I, y is in j. So this is the sum of two ideals. And there's also a product of two ideals. So I bracket j, which is, now this is not just the set of commutators. As he explains an example at the end of this section, this chapter, if you just use the set of commutators, it's not like, it doesn't work. So you have to do span here. So it's the span. There's some more obvious things. Like if you just had the set of, I don't think you'd be guaranteed that it's a subspace even if you just used all commutators. And by commutators I mean brackets, I should say. Bracket of x and y such that x in I, y is in j. How am I doing, Audric? Am I where I'm supposed to be?
Yeah, I am trying just to catch up here on setting up. So
Okay.
yeah, you look fine right now.
Oh, don't worry. We have not done anything substantial yet. I'm just getting the starting definitions in chapter 2 out.
So you're not recording yet?
No, we're recording.
All right. Okay, good.
Let's see here. So his claim, and I guess, so, all right, so his exercise 2.1 is to show that the sum of ideals is an ideal. All right, that's an exercise. But he actually has the proof of the bracket of two ideals being an ideal in this sense. Well, it's the span of the brackets, right? But let's just call that the bracket of the ideals. So let's see here. Let's see if we can work through this. So this is let's look at this problem. Let's try to get into some details here. Why is this an ideal of L? So what do we need to check? So let me call this thing K for the sake of discussion, all right? So note, K is a subspace of L by construction. Why is that? Because the span is a subspace, right? So we have the span is a subspace theorem from linear algebra. And okay, so then next thing we need to let, let's say X is an element of the bracket of I and J, or X is an element of K, and let's let Y be an let's let Z rather. Let's Z be an element of L. Then X is equal to what? It's equal to a sum over, let's say, Cij of bracket X sub I, Y sub J, where X sub I is in I and Y sub J is in J, right? That's just the definition of what it means to be in K, right? In this bracket of I and J. So then I want to look at the commutator of X with Z, right? And I'd like to show that. So, by the way, up here, I could have done this, or I could have done what? Either way is equivalent, right? Because of the properties of the bracket. So I think just the way I've set this up, it's going to be more convenient for me to look at X with Z, all right? So that is going to work out to bilinearity, not bilinearity, although I should say by bilinearity in the first slot. So I'm an idiot. Cij bracket of bracket xi yj comma z, right?
That makes sense, but do we want to flip the z and the x and the, to what you're saying, oh, never mind.
Yeah, that's why I said that, because I knew I was, my bad.
No,
I was going to be late. All right, so now we need to remember what's the Jacobi, maybe I should write the Jacobi identity at the top of the board, actually. All right, so the Jacobi identity says, I'm going to write it in terms of ABC. It says bracket of A, bracket B, bracket C, plus bracket B, bracket C, bracket A, plus bracket C comma A comma B is equal to 0. I mean, this may not be how it's written in the book, but this is the way you could write it, okay? There's a couple different, like you could put the bracket first or second, but you need this pattern. So as I look at, and I see that that doesn't serve my purpose, does it? Fine, minus the sum Cij z xi yj. All right, there we go. So now I'm going to think of that as being the first thing up there. So I can trade that for the sum of Cij parentheses xi comma yj comma z plus yj comma z comma xi by Jacobi. Right, so I'm solving for the bracket that I'm given in terms of the two that I'm not given. And the reason the minus went away is because I used the Jacobi identity. All right, so now notice what goes on here. What's the story? Well, this right here is an element of what? Where's z? Z is in the Lie algebra. Y is where? In J. We're assuming J is an ideal. So this is an element of J. Likewise, this is an element of I, because I is an ideal. But then, since you've got something, I mean, you can go any way you want here. Let's see here. I mean, technically, this bracket, you're taking J, something in J bracket with something in I. So it's in I again, but you could also say it's in J again. In fact, it's in the intersection of the ideals, truth be told. But to our purposes, this is an element of I. And because Yj is in J, we have something in J bracketed with something in the Lie algebra. So we can say that this is also in J rather. I mean, the truth of the matter is, you could say that this is in I. I mean, I can be more greedy. They're actually both in the intersection. Oh well, we don't even need to use that. The point is that they're both. I mean, that one's in I, that one's in J. Oh, you're right. My bad.
You could say, well, like you just did, that the intersection is an ideal, and so since an ideal is a closed,
well,
subgroup.
What I was trying to argue is that let me just so all I'm trying to say here is that at this point it should be clear that the bracket that we're looking at here, we've got something in I with something in J bracket, right? And over here again you've got something in J with something in I, right? But we can throw a minus in here, right?
Yeah.
I can put a I'm gonna put a minus here, all right? And I'm gonna flip these.
Yeah.
That's what I should do. Okay, because then this is an element of J, right? Element of I. So look what I've got. I've got a linear combination of things where you're bracketing things in I with brackets j. So by definition, this altogether is an element of ij, which then implies that this guy is ideal of L, right? So we have three ideals that we can think about here. The intersection of ideals is an ideal, the sum of ideals is an ideal, and the bracket of ideals is an ideal. I've only given you proof for the bracket one though, all right? The sum one is an exercise, and yeah. Okay, so here's what I was looking for. Because I tell you what, this drives you nuts when you forget about it later. So definition, L prime is equal to LL, right? So we're talking about the span of x and y such that x and y are elements of L. This is called the derived algebra. He says it's the derived algebra of L prime in the book, but I think that's a typo. Derived algebra of L would probably be more reasonable. Yeah, otherwise like, what? So this is the derived algebra. So it's sometimes also called the commutator algebra. And if the Lie algebra we're looking at is abelian, then of course that's 0, right? Okay. So next up, he wants to talk about quotient algebras, all right? So we need to talk about quotient vector spaces. And you guys may not have had much experience with that before, right?
Not particularly in the context of vector spaces.
Right, so here's the definition. If W is a subspace of a vector space V, then V mod W is the set of cosets of the form x plus W such that x is an element of V. So this is the quotient vector space. And how do you scalar multiply? So like if I have x plus W plus y plus W, you do, shockingly, x plus y plus W. So you just add the representatives. And scalar multiplication, also scalar multiply like that. Now, that begs the question.
Turn me a bit when you get a chance.
Yeah, sure. That begs the question, is that well defined, right? I don't think this is even in Erdmann and Wilden because this is before I think this is before their book, really. So if that's how we define quotient vector space, it begs the question, are those really well defined, right? Because, well, the fundamental issue, even before that, is when are two cosets equal, right? So, like fundamental lemma, if you will, x plus W is equal to x prime plus W if and only if the difference of x prime and x is an element of W. Now, this you've already proved in group theory Because after all, the additive structure of a vector space is an abelian group, right? And every abelian group is normal. Therefore, the quotient group is well defined, and that's what this is. The quotient vector space is just that. But it's got more structure, right? Because it's also a vector space, so we have also defined scalar multiplication, right? So maybe there's something to talk about there. Do you guys want me to talk more about the fundamental lemma, or are you comfortable with me going on?
That's fine. This scalar multiple.
The scalar, yeah, let's look at the scalar multiple. So if x plus w is equal to x prime plus w, right, then if we look at cx minus cx prime, we get c times x minus x prime, right? Which is an element of w, since w subspace, right? Thus, cx plus w is equal to cx prime plus w, which shows you that the definition of scalar multiplication is independent of our choice of representative, which is to say it's well defined. So, yeah. So at the moment, I'm just blathering about the linear algebra here, right? But we're interested in the Lie algebra, so we want to talk about, what do you think? I mean, the whole idea here is that if we have an ideal, then we're going to be able to define a quotient Lie algebra, all right? And we're going to be able to define a bracket on that quotient Lie algebra. And the uber closure of the ideal is precisely what we're going to have needed in order to make these things well defined. Are we good? Any questions, Audric?
So far, okay.
Okay, cool. So how are we going to? So let's suppose let's see here. Bop, 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 bop. I guess we can. All right. So definition, suppose I is an ideal of Lie algebra L over field F, then L mod I is equal to x plus I, such that x is an element of L, right? And we define the bracket of x plus I with y plus I to be what? Bracket what? I mean, it has to. Right, we just do bracket of x and y plus I. Hopefully that makes sense. So for it to make sense, what do we need to check on? Right. So yeah, we need to check on well-defined. And then, of course, also you need to check that, it has the right bilinearity, that it has the right Jacobi identity. But those other things actually pretty much are pretty easy to see. They come from the way that the addition on a quotient space is defined. So basically, like, once this is well defined, proving that the quotient space is a Lie algebra is pretty much immediate, because of the way that the addition is defined over here, and the fact that we have in the way the bracket is defined. Okay, so what we should do is suppose x plus I is equal to x prime plus I, and y plus I is y prime plus I, right? And what we want to look at is then the bracket of x prime, y prime, basically, right? Now, let me point out something. So, because x prime minus x is an element of I, and because y prime minus y is an element of I, we can find particular elements, right? We can write x prime is equal to x plus, like, let's say, little I, and y prime is equal to y plus little, let's say, j, where I and j are elements of the ideal. And so in view of that, this becomes actually what? This actually becomes, x plus I, y plus j. And then we can use bilinearity of the bracket, and we get xy plus I with, I with y plus j, right? And I'm tempted to use bilinearity of the bracket, but maybe I don't need to. Why? What is this right here? Think about it. So you've got something in I, and this is something in L, right? But I is an ideal. Right. So since this is a bracket of something in the ideal with something in the algebra, altogether this is an element of the ideal again, right? So therefore, x prime y prime minus xy is an element of I, which is what we were setting out to prove. See, then that proves that this is independent of our choice of representative. Yeah. So because these are, yeah. That suffices to prove that the bracket's well defined. Now, they have a more lengthy way of showing it. I don't know. I don't think I'm wrong. It does worry me the book seems to have a longer argument, but, well, if I'm wrong, eventually the internet will correct me. Let's see here.
The book's just the trivial sake of identity that you're talking about.
Oh.
Part of it, the length of it or something.
Maybe. Okay, so next up here, he introduces the isomorphism theorems. Right, so there's 3 isomorphism theorems to know about. The first, the second, and the third isomorphisms. The first is the one I remember. I'm not a very good algebraist. I only remember one of my 3 isomorphism theorems, right? Although if you pay me enough money, I could figure out the other 2. If put under pressure, I could find them. But so here's a theorem, which we will not prove. We're just going to state it. All right. So if phi is a homomorphism of Lie algebras from L1 to L2, let's say a Lie algebra homomorphism, then the kernel of phi is an ideal of L1, and the image of phi is a subalgebra of L2, all right, and we have that L1 mod the kernel is isomorphic to the image of the homomorphism. So that's part A. Part A is that. And part B, he has, if you have ideals I and J, then if you look at I plus J, so the sum of the two ideals, which is of course an ideal, and you quotient by J, that is isomorphic to, what is it isomorphic to? It is isomorphic to I mod the intersection of I with J. And then C is kind of like a little bit less surprising in terms of like the pattern, because C is, if you have I and J are ideals and J contains I and J ideals with what did I just say? J contains I, so I is a subset of J. Then J mod I is a ideal of L mod I, and if we take L mod I and then mod by J mod I, it's isomorphic to, shockingly, L mod J. So this is sort of a victory of heuristic fraction notation. But so these are respectively the first, the second, and the third isomorphism theorems. Now, let's see here. So these are all like pretty natural things to prove in linear algebra. Like it's a good exercise to prove that these theorems are true, you know, for linear algebra. Let's see here. To see, let's see why the kernel of the homomorphism is an ideal. Let's work on that one. Okay. Any questions, Audric?
None so far. I'm just trying to catch up right now.
Okay, cool. So we're just gonna kind of, we won't prove all of this, right? We're just gonna, I'm gonna try to pick some little piece and tinker with it. All right. So the piece I'll pick on is kernel of phi an ideal. So first of all, that begs a question, which I think every student grapples with when they're first dealing with this course, which is, what's the definition of the kernel anyway? And so what, well that,
That's the identity.
what's that? Everything that what?
And that's the identity.
Yeah, it's internal, right?
Yeah, so x and L such that phi of x maps to the identity. Now the identity here is 0, right? So what is that? Yeah, so I mean that's the definition, right? Okay.
But phi is a Lie algebra homomorphism.
Right, yeah, phi is a Lie algebra homomorphism. So this is by necessity a subset of L1, right?
Yes.
Okay. So what we should do then is we should let, x be in the kernel and y be in L1, and we should look at the bracket, right, of x with what? With y. We should be able to show that this is an element. We'd like to show that this is an element of the kernel, right? So y is the bracket of x and y, an element of the kernel. Question mark, right? See, the question mark is the thing my students so oftentimes do not write, and that is why I take points away from them. But that question mark makes all the difference in the world, because that's the difference between assuming the point and not. Okay, so to check if this is in the kernel, we need to feed it to phi. So this would be, I should check what is phi of this, right?
Well, if it's already homomorphism, so the bracket phi of x is phi of y.
Okay, very good. And what is phi of x equal to?
0.
0. Okay. So that's equal to 0, which of course, therefore, xy is indeed an element of the kernel of phi. And since x and y were arbitrary elements of the kernel and the Lie algebra respectively, this shows that the kernel of phi is an ideal. So that's not bad, right? So one of the things to notice about this isomorphism theorem is it is an isomorph. We are talking about isomorphisms of Lie algebras, right? So this is like Lie algebra isomorphic. All right. And this is a Lie algebra isomorphism, and this is a Lie algebra isomorphism. So, So the proof of this should show that the brackets preserved as well, right? And so he attributes it to, I should say they attributed it to exercise by part 2 of exercise 2.3. So part 2 of exercise 2.3, the moneymaker here is that the projection map from, I've already forgotten it. Okay, so yeah, from L to L mod I is a Lie algebra homomorphism, all right? And that's probably worth looking at. Let's look at this carefully, okay? So this is the canonical quotient map. This is the coset map. So the definition here is pi of x is equal to x plus I. All right? So then the question becomes, why is this a homomorphism, right? So let's look at it. So I'm about to do a really easy homework problem for you guys. So we're supposed to look at the bracket, right, of pi of x with pi of y, I guess. I mean, you could start on whichever side you want, but we'd like to show that that's pi of the bracket, right? But what is this? That's the bracket of x. Right, it's practically the stupid definition of the bracket on the quotient space, right? By definition, this is bracket of xy plus I, which, by the way, is pi of the bracket. So there you have it. The quotient map, the natural quotient map, is in fact the Lie algebra homomorphism. Of course, you also need to check that it's a linear transformation, but that can be shown. Right, yeah. Essentially, it comes from the fact that the quotient vector space construction is well put, you know, yeah. All right. Let me move along. So he has some, he's got a paragraph here where he talks about if I is an ideal, he has an example concerning the trace going from GLN to F. That might be worth, let me just write that up. Yeah. I should write that up. That one's a nice example. Let me not skip that. My bad. Sorry, Audric. We got pushed into the bad room. There. Can I erase the
picture of it?
Oh, I'll erase at the top.
No, you're fine. You can erase all of it. Yeah.
Okay. There you go. I left the part which is most recent. Okay, so he says, so example 2.3, he's like, look at the trace of an n by n matrix. So for us, I guess this will be example 1. Okay, so we can look at the trace as a mapping from GL and F to F. Right? And so if you calculate the trace of the commutator bracket, because I do actually mean commutator bracket this time, you've got the trace of AB minus BA. By linearity of the trace, this is trace of AB minus the trace of BA. But by the properties of the trace of AB is the trace of BA. And so you get 0. And 0 is in fact the trace, that is in fact the trace of A commutator with the trace of B. This is in F. Because in F, F is a abelian Lie algebra. This is very silly, but this is one-dimensional abelian Lie algebra. Okay, so by the way, check this out. If C is an element of F, right, then the trace of C E11 is equal to C. Now E11 is the matrix with a 1 in the 1, 1 spot and 0 everywhere else. This is available in GLNF, period. Right? So that matrix has trace C. That shows you that trace of GLNF is equal to F. In other words, the image of the trace is everything. So trace is a surjection onto the field. Because you can make any matrix have whatever trace you want. The simple calculation. So I'm showing you that it's an onto map. The trace is onto. Okay. So then we can apply the first isomorphism theorem here. So the first isomorphism theorem, what's it tell us?
I think you've read it already once. That if you modify the kernel, it's isomorphic to the
Right.
to the normal subgroup.
Right. So in this context, we have what? We have GLN F mod the kernel of the trace, right, is isomorphic to the image of the trace, right? The image of the trace. Right. And so let's put this into less opaque terms. GLNF, what do we call the kernel of the trace? That means the trace is zero. What's the trace? Which trace zero? We call that the special Lie algebra, right? That's SLN. So if we take GLNF and we mod by SLNF, we just get F. So this gives you, an interesting comment, I suppose. I mean, there's various things you can see from this, like, for example, the dimension of the general linear algebra is one less than. Yeah, we've mentioned that before. I mean, there's a sort of a more. Yeah, I should mention, by the way, like if you've got a quotient vector space, right? The dimension of the quotient vector space, guess what? It's equal to the dimension of V minus the dimension of W. That's how it works. The way to construct a basis for the quotient vector space is to take, basically you just take a basis for the subspace you're modding by, and extend it to be a basis for the whole space. Everything in the extension you can prove gives you a linearly independent set of a set of representatives. So like, let me write that down. Let me write that down. You guys have not seen that. You guys have not seen that. So like, the way to find a basis for the quotient space. So we got basis. Let's talk about that for a second. Basis for V mod W. So this is not really the intention of this book. All right, I'm adding some background a little bit here. If you're interested in this. So what you do is, if you've got W a subspace of V, right? That means that you can, I'm assuming we're in a finite dimensional context at the moment, okay? So if beta W equals to, say, W1, W2, Wm, basis for W, right? Then by the theory of bases for linear algebra, we can extend this to a basis for the whole of the vector space, right? You can extend to beta, let's say W1, Wm, and then let's say V1, V2, V, n minus m. So here I'm assuming that the dimension of V is equal to n, and span of beta is V. See, there are m plus n minus n vectors here, which is to say there are n vectors. So you can prove that beta V mod W equal to, let's say, V sub I plus W, such that I equals 1 to n minus m is linearly independent spanning set for the quotient space. And so once you do that, then you've proved my claim over here. Yeah, to prove this, if you take the sum, I equals 1 to n minus m of ci times vi plus w, what's that equal to? That's equal to the sum I equals 1 to n minus m of CIW, CIVI plus W, right? Now we're setting that equal to 0 because we're studying linear independence of this set, right? So you set it equal to 0 in the quotient space, which means you set it equal to 0 plus W. 0 plus W is the 0 vector in the quotient space, okay? And to say that is to say what? That's to say that the sum I equals 1 to n minus m CIVI is an element of W. But W, mind you, is the span of W1 through Wm, right? So that forces this to be the trivial combination, because to say otherwise is to imply linear dependence in your original basis.
Oh.
See, because these W's paired with these V's forms a basis. So if this linear combination is in this span, it has to be 0. If this is non-trivial, that immediately implies a linear dependence in your basis.
Yeah, okay, gotcha.
Therefore, that must be the 0 combination, right?
Yeah.
And then what does that say? How do we get that?
Because they have to be, the least-divides themselves.
Right. Then by linear independence of the extended part of the basis,
Okay.
we get, so it's a couple different things going on, like the independence of the extension from the original part, as well as the independence of the extension, yeah.
That's kind of cool. Thank you.
Yeah. But it also, in addition to just being an interesting like dimension formula, it also actually shows you how to set up a basis for a quotient space if you're called to do it. It's pretty simple. You just find a basis for your space, and then everything that's not needed to form the basis for your subspace, those end up being the things that correspond to representatives of the basis you're interested in. Ay, ay, ay. Let me go on. But anyway, the Section 2.3, he talks about correspondence between ideals, and he talks about how ideals are nested. If J is an ideal of L containing I, then J mod I is an ideal of L mod I. Conversely, if K is an ideal of L mod I, then the set J equals to, okay. Well, that sentence doesn't make sense, but whatever. And one can readily check that J is an ideal of L that contains I. So anyway, we'll deal with this when it comes to us, okay? When we need this stuff, we'll talk about it again. Audric, what's going up there, that's essentially the Galois correspondence business, if you're wondering. Yeah. It's something like, I mean, the way ideals nest and things, it's a little bit counterintuitive. You just kind of have to, I think it's better for us to just bring it back up again when we do. Okay, so now we're into chapter 3. Chapter 3 is on low-dimensional Lie algebras. And so just to give you a quick overview of what this chapter does, is he just looks at different possibilities for the bracket of two things to describe what's possible in dimension. I mean, dimension 1 is easy. Dimension 1, the bracket has to be 0. So that's kind of it. So as he says, any one-dimensional Lie algebra is abelian. And you can have a two-dimensional Lie algebra, then all you have to do is, define what happens with the bracket of x and y, and then you've pretty much uniquely defined what's going on. So he explains that. Then for dimension 3, it gets more exciting because, you can have. So in each one of these, in this chapter 3, he's looking at what is possible for the derived subalgebra. That's essentially what he looks at, what they look at in chapter 3. So when you get to dimension 3, the derived subalgebra starts to be more interesting because the derived subalgebra could either be one-dimensional or two-dimensional, because the derived subalgebra will be a subalgebra of L. All right. So anyway, as he explains, you could have the Heisenberg algebra, or you could have something he doesn't give a name for. He says, theorem 3.2, that F be any field, there's a unique three-dimensional Lie algebra over F such that L prime is the derived algebra is one-dimensional, and L prime is not contained in the center of L. And this Lie algebra is the direct sum of the two-dimensional non-abelian Lie algebra with the one-dimensional Lie algebra. On the other hand, if the derived algebra is a subset of the center, then that's the Heisenberg algebra. All right. Let's see here. And then the other possibility, of course, is that the derived algebra is two-dimensional. And he explains in section 3.2.3 that actually gives you many, many possibilities. He says there are infinitely many non-isomorphic such Lie algebras. And he derives a parametric family of them, I think, in this proof on page 23, essentially. So and then, of course, the other possibility is that the derived subalgebra is equal to the whole algebra. In other words, the derived subalgebra is three-dimensional. All right. And what's he say there? He says, well, if that's the case, then up to isomorphism, you're just talking about SL2C. Right? SL2C is the Lie algebra such that the derived subalgebra is equal to the algebra again. Okay. Now, I have spent, in previous time I tried to teach this course to a few students, I spent several hours going through all of that, and I found that it wasn't that exciting, so I'm going to go on. So if you'll forgive me for being a little bit of a... Is that okay, Audric?
Yeah, you're good.
Okay. I think that the arguments in the book are solid and you can follow them, So it is interesting, right? Because it's already more interesting than groups, right? Let's just take a second to sort of smell the roses here for a second. If you talk about groups of finite order, right? Up to order 3, what's the story? Yeah, up to order 3. So groups of order 1, you've got the trivial group, right? The group that just contains the identity. Yay. How about a group of order 2? What are we talking about? Up to isomorphism of groups. Yeah, just Z2 or the roots of unity, like the square roots of unity, you got different models for it, but it's the finite group of order 2. Someone should write a song about it, right? Let's see here. And then how about